Now, we looked in the first lesson our generalization of series. We've come across Taylor series and many other series, but specifically to Maclaurin series to give you an idea of what you can possibly do with any types of series. We're looking at the Maclaurin series. So continuing with our examples, in these examples we want to find a series of ascending powers, just different ways in which we can ask questions of the function sine squared of x. And with our series, we can go on to an infinite number of terms. However, in this example, we want to stop at the term containing x to the power 6. So with our setup of finding Maclaurin series, and I would like to stress that this is the manner in which I am lecturing. You don't need to set it up as a table like I am doing. In fact, you can go directly to the formula for Maclaurin series and get your answer. So why would I do it the way that I'm going to do it now? Well, let's see. So in my solution, I am going to let f of x equal to sine squared of x. So if f of x is sine squared of x, according to the Maclaurin series, I need to find the function at 0. And working that out, sine squared of 0, that gives me 0. Now I need to find my derivatives, the first derivative. Now, do you recall? And this trig, the powers of trig functions always seem to be a problem. I guess another way of writing this would be sine of x all squared, which means using the chain rule, I must first use the power rule and then differentiate sine x, which I'm going to do. Getting back to this, 2 times sine of x, that's the derivative of the exponent 2. Now I differentiate the arguments of sine of x squared, which is cos of x. So there I get my first derivative, 2 sine of x times cos of x. And of course, I must now find the first derivative at 0, substituting 0 right through. You can use your calculator. What do you get? 0. Once again, just look at the values that you're obtaining, which indicates that the first two terms are 0. So we don't have a term yet, which means I must continue with our derivative. Now, at this point, look at this carefully. If I want to differentiate 2 sine x cos x, and I will do that on the side. So what is the derivative of 2 sine x cos of x? Well, to do that, I can use a product rule. Yeah, I'm going to use the product rule. 2 sine x cos x. So the derivative sine of 2 sine of x is 2 cos of x. Then you leave cos of x plus. Now you leave 2 sine of x and differentiate cos of x. However, you can be a bit more intuitive as far as our trig functions are concerned. Look very carefully at 2 sine of x cos of x. Do you realize that is simply the expanded form of what function? That's right. From schoolwork, that is simply sine 2 of x. So it's the same function, but written in a simpler form. So whether I differentiate using the product rule or whether I differentiate sine 2x, I'm still going to get the same answer after a lot of manipulation. However, differentiating sine 2 of x is much easier, and I will continue using exactly that. So differentiating sine 2 of x, recall the chain rule, first the sine, then 2 of x. So if you differentiate sine, that gives you cos, and the argument doesn't change, then differentiate 2x, the derivative of 2x is equal to 2. I get 2 cos 2x. And the second derivative at 0 will give me 2. Now I'm just going to continue. So for the rest of the derivatives, let's use the chain rule accurately. Derivative of cos 2x is minus sine 2 of x. Then the derivative of 2 of x is 2 multiplied by that 2, the coefficient, I get minus 4. Sine 2x, substitute at 0, I get 0. Now I go on next derivative, the fourth derivative. You can check all of this. I get minus 8 cos 2 of x. The fourth derivative at 0, negative 8. Fifth derivative, 16 sine of 2x. Fifth derivative at 0, 0. Sixth derivative, 32 cos 2x. Sixth derivative at 0, 32. So I had to go and continue up to the sixth derivative. Why? Because the question required to go up to the term containing x to the power 6. And why would I stop at x to the power 6? According to the Maclaurin series, if you go to the formula, well, let's write down the formula of the Maclaurin series. Just a quick recap. The Maclaurin series formula was f of x. Do you recall that? F at 0, first derivative at 0 times x, second derivative at 0, 2 factorial x squared, third derivative 0, 3 factorial x cubed. Okay, you know the pattern, and continue. Therefore, my sine squared of x, I'm simply going to substitute f at 0. There's it here, 0. First derivative at 0 is also 0 times x. The next derivative, second derivative, at 0, 2 over 2 factorial x squared. Third derivative, 0. Continue. Fourth derivative, minus 8. How many, what fourth derivative therefore? 4 factorial. What power? X to the power 4. Plus fifth derivative, 0. Sixth derivative, 32. Sixth derivative, therefore 6 factorial. What power? X to the power 6. Now I can stop. And then simplify. What am I left with? X squared minus, and yeah, we're going to work this out. Minus 8, just on the side, minus 8 over 4 factorial. You have a calculator, You can work that out. That's going to give me minus x to the power 4 over 3, and in the last 32 over 6 factorial, I get 2 over 45 x to the power 6, and there is the series of sine squared of x to the term containing x to the power 6. Right, now to emphasize, we are using Maclaurin series. That's the formula for the Maclaurin series. How do we find the coefficients of the terms of the Maclaurin series? By repeated differentiation. And I'm going to stress now repeated differentiation. What does it imply to you? Revise your differentiation concepts, theory, and procedure. So I could get product rule, quotient rule, and so on. And whenever you can, as in our case, make a differentiation process easier, you do so. So we took sine, or rather 2 sine cos x, and wrote it out as sine of 2x, and that made our differentiation process a lot easier. Now, using the Maclaurin series, I then obtain standard series for a number of terms. And these are standard series of which you need to remember, to recall whenever needed. The first one, sine of x, on the left-hand side, that's the expanded form, which is what we really would like to do. And that's the closed form, or an abbreviated form, using, of course, my sigma notation. In most cases, well, in all cases in 1b, we would be looking for you to recall the expanded form. Now, how would you remember this? Well, the sine of x is also known as an odd series, and you can see why. Look at the indices of x, x to the 1, x cubed, x to the 5, x to the 7, x to the 9, odd numbers. The factorial notation is also odd, so it's x cubed over 3 factorial, x to the 5th over 5 factorial, and it's an alternating series. The cos x is also known as, yes, an even series, except its first term is 1. So it's very similar to sine, except instead of using odd indices, we get even indices. And it's also alternating. Sine of x, how can you remember that? Well, it's actually quite easy. The terms are virtually the same as sine of x. Well, they are the same. So what's the difference? This is not an alternating series. All the terms are positive. The same with cos of x. Very similar to cos of x. All the terms are exactly the same, except this. All the terms in this case of the cos are all positive. E to the x, well, e to the x is virtually a combination of sine and cosine. So it's all the terms, both even and odd, and it's not alternating, they're all positive. There's e to the x. I also have standard series for ln of x, standard series for tan of x. Now, just a precaution here. Although these are standard series, you may in fact be asked to prove. So all of these can be proved using the Maclaurin series formula. In some cases, depending on the question, you will not be asked to prove it. You will be asked to use it immediately. So what do I mean by that? Well, let's have a look and look at these very carefully. Now, one of the extremely important aspects of mathematics is to recognize that a given series or a given term, expression, formula that you are asked to work with may be very similar that of an expression or form of equation that you've come across before. And instead of working it out from first principles, like in our case, Maclaurin series. Maclaurin series, if you are asked to find a series by using Maclaurin series first principles, you'd have to do repeated differentiation. But let's look at this question. It says if f of x is equal to e to the x, find the series expansion for f of 2x. Now, it's not stated here that I must use Maclaurin series. So how do I go about finding a series expansion for f of 2x? Well, they specifically state, start with f of x equal to e to the x, which I have over there. Now, immediately below that, I'm going to write f of 2x. And you know what that means. It simply means replace x of the original e to the x by 2x. So wherever you see x, replace it by 2x. And I'm going to emphasize here so that you don't make a silly error. Place that in brackets. Now, we could use another variable for x, but generally in most textbooks, standard series are the use of x instead of any other variable, any other letters used. So what does that imply for us? We must realize that to generate a function, another function, from a standard function, all you have to do is replace x there by 2x. So the series stays the same. The 1 will remain 1. But wherever I see x, what do I replace it with? 2x. So I'll continue with that. The next is 2x squared over 2 factorial. Then 2x cubed over 3 factorial. And you see the pattern. 2x to the power 4 over 4 factorial, and so on. And now all I have to do is simplify that. So I'll get 1 plus 2x. Now I would like you to simplify each of these terms. So 2x all squared, for example, 2x all squared over 2 factorial gives you 4x squared over 2 times 1, which is 2. Simplify that, I get 2x squared. So this term is plus 2x squared. And you can check the rest. This is 4 over 3x cubed plus 2 over 3x to the power 4. So that is a series expansion of f of 2x. The next example, find a series expansion for ln of 1 minus x squared. Again, you're not forced to go from first principles, which I suggest you don't do, because if you find the derivative of ln of 1 minus x squared, you'll have to use the chain rule, and you're going to get, you can double check that. What is the derivative of the ln of 1 minus x squared? Well, this will be nice because what we can do, we're actually revising. So first it's ln, so it's 1 over 1 minus x squared. then the derivative of 1 minus x squared is minus 2x. Now imagine repeatedly differentiating this fraction. Quotient rule, quotient rule, quotient rule. You will continue and it will be a pretty long process. However, what we can do in this case, because they don't stipulate we have to use Maclaurin series, I can rearrange the ln of 1 minus x squared. So the ln of 1 minus x squared, I want to rearrange it in such a way that the 1 remains a 1 and the plus remains there. So I have to look at x and decide what is x actually replaced by to get minus x squared. And I'm going to write it here. So that will be the ln of 1 plus, what do I have to do? In other words, plus 1 times what will give me minus x squared? That's right, it will be minus x squared. And that is what occurs in this particular case. I will have to replace x by minus x squared. So that is the replacement in this series, which means wherever I see x, I now replace it by minus x squared. And of course, like I emphasized, in brackets. So this becomes, there's my x there. What do I replace it by? Minus x squared. Then minus a half. Replace it by minus x squared. Then a third, and so on. Every single term replace by minus x squared. Minus a quarter, minus x squared. Okay, this first one is x, then x squared, all squared. And with the 1/3, what's the index? All cubed. With the minus a quarter, what's the index? All to the power 4. Then 1/5 of minus x squared, all to what power? To the power 5, and so on. Let's just put that out of the way. And all I have to do now is simplify, and you can check that simplification. I get minus x squared minus a half x to the power 4 minus 1/3 x to the power 6 minus 1/4 x to the power 8. Okay, we can stop there. Therefore, the ln of 1 minus x squared has a series expansion given by x squared minus a half x to the power 4 minus 1/3 x to the power 6 minus a quarter x to the power 8. Right. Now, a very, very important series is the binomial series. And the term itself tells you exactly how many terms. Binomial, 2 terms. Now we're going to go through this process of finding a formula for a binomial series. And this is a very particular binomial series that we are going to do. It is the binomial series 1 plus x to the power n. And of course, it doesn't have to be 1. It could be any value. In fact, in most textbooks, they generalize it where these terms here could be anything. We just want to make sure that you can write down a binomial series. And that is why we're only going to look at binomial series of this form, which is 1 plus x to the power n. So whatever you're given, you reduce it to that form. For example, what am I talking about? If you get 1 plus x to the power 20, we noted that in this case, x stays x, Okay, let's just remove that. The x remains an x, and the x stays x, and n is a 20. Now look at this here. Square root of 1 minus x. It has the same form as a binomial series. 1 plus x to the power n. Can you figure that out? Why do I say it has the same form? Because I can rearrange. I can write the square root of 1 minus x as 1 minus x to what power? To the power of. Which in turn, I can rewrite as 1 plus a minus x to the power of half. And there's your binomial series. And what has happened? The x is now replaced by a minus x, and the n we have to replace by a half. Now I can go to many different types of examples. You need to see the connection to the binomial series. But we're talking about a binomial series. Well, how do I go about using it? Well, we're going to generate that formula of the binomial series by using Maclaurin series expansion. And what does that mean? It means I have to go through that same process. If f of x is equal to 1 plus x to the power n, then substitute 0, 1 plus 0 to the power n, 1 to any power is 1. Then I must find the first derivative. And here it's the chain rule. So first it's n around the argument 1 plus x, and then subtract 1 from the index. So it's n times 1 plus x to the power n. First derivative at 0, that's equal to n. Substitute x equal to 0. I'll get n times 1. And remember 1 to any power. So just to substitute 0, I get n times 1 plus 0 to the power n minus 1, which is n times 1 to the n minus 1, and 1 to any power is equal to 1, so I'm just left with the n. Now look carefully. Look at the second derivative now. I have to take this n minus 1 and multiply there. So I'll get n times n minus 1 to the 1 plus times 1 plus x, and now I must subtract 1 from n minus 1, n minus 2. And my second derivative at 0 will be n times n minus 1. Can you see a pattern emerging? Let's look at the third derivative. It will have to be n minus 2 times whatever's before 1 plus x. So it will be n times n minus 1, yes, n minus 2 multiplied by 1 plus x, subtract 1 from the index, n minus 3. And what do you think is the third derivative? At 0, n minus 1, n minus 2. So I am obtaining the coefficients of the terms. And we can go ahead and do the fourth derivative. Let's just do that quickly. So it's a repetition. If it's to the power, so it'll be n minus 1, n minus 2, n minus 3, 1 plus x to the n minus 4. And what do you think is the fourth derivative at 0? How far will I go? N minus 1, n minus 2, n minus 3. So fourth derivative, you stop at n minus 3. Now substitute into the Maclaurin series. Do you remember what the Maclaurin series looks like again? If I'm repeating this so that you can recall it without having to look at your notes. Imagine You don't have to look at notes. Everything will be memorized. F of x, Maclaurin series. What's it? F at 0. Do you recall that? First derivative at 0, x. Second derivative at 0, x squared. Third derivative, 0 cubed. Do I need to continue? Now all I have to do is substitute. So my binomial series, 1 plus x to the power n. What's f at 0? 1. What's the first derivative at 0? N times x. What's the second derivative at 0? N minus 1 over 2 factorial x squared. Third derivative, n minus 1, n minus 2. So if it's a third derivative, we stop at 1 less than that, n minus 2, but it's the third derivative, so it's 3 factorial. And what's the power? X cubed. Just write on the next one, what do you think it is? N minus 1, where do I stop? That's right, but it's the fourth derivative, so it's over 4 factorial, x to the power 4. And there is the series expansion for a binomial series. Now, how are we going to use this? Well, look carefully at what I started at the top here. There's a binomial series. Wherever I see x, I put x. Wherever I see n, what do I put? 20. Or in the next case, x I replace by minus x, n I replace by half. And where do I replace it? Right here into this formula. So let's see, have you come across it before? Think carefully. It's not a trick question. You've used it so many times in school. Okay, what am I talking about? Well, let's have a look. Okay, there is the binomial series formula. Which you need to recall. But more importantly, you need to know how to implement it, how to use it. So 1 plus x. So what about 1 plus x squared? Oh, I think you remember how to do that, eh? 1 plus x times 1 plus x, multiply out. What do you get as an answer? 1 plus 2 times x. You multiply those two and double it, plus x squared. Okay, pretty easy. But what if I tell you that I want you to find 1 plus x squared using the binomial series formula? Well, let's double check. Does it have the form of the binomial series? Yes, it does. The 1 is still there. The x is still there. So the x stays a x. But the n must be replaced by 2. So let's do that. So the formula, the first term is 1. There's nothing to replace there. The next term has got an n times the x. Our n in this case is a 2, and then the x. The next term is n, which is 2, times 2 minus 1 over 2 factorial x squared. And guess what? Simplify that, and what do you get? 1 plus 2x plus x squared, exactly what you did at school. Now, the next 1 plus x to the power 4, I'm going to use the binomial series. X stays x, n is replaced by 4. So if I substitute that into the binomial series formula. Wherever I see x, I leave the x. Wherever I see n, I put 4. I will get as an answer 1. Then 4x, 6x squared, plus 4x cubed, plus x to the power 4. Once again, you can check that by substituting into the formula. Now you could also use, in this case, I'm pretty sure many of you have come across Pascal's triangle, which is fine. If you start here and go 1 and 1, 1, 1, then you're going to add, you get 2, but that's only to the square. What if I ask you to go to a power 20? Whoa, you're going to have to write down Pascal's triangle right down to 20. Well, if you know the binomial series formula, you don't need to do that. You can generate every term simply using binomial series. Now, when you look at binomial series, which probably many of you are going to do, and you're going to Google it, you're also going to come up with what is known as the binomial coefficients. And the binomial coefficients is given by this particular formula, which I am not going to do, and you are not expected to know. What are they? They simply a formula written in this form to find the coefficients here of the different terms. Right, now having said that, how can we apply the binomial series? Well, let's have a look at this. Find the binomial series expansion for the square root of 1 plus x cubed. Right, our binomial series expansion for the square root of 1 plus x cubed. Well, do you recall what we've done? How we can rearrange this term? The square root of 1 plus x cubed. Is it a binomial series form? Yes, it is. There's 2 terms. How else can I write it? 1 plus x cubed. Or to what power? To the power half. Now, if the series expansion of a binomial, the original form is 1 plus x, that means x is replaced by x cubed, and n is replaced by a half. And that's exactly what we do. Wherever we see, so let's just go back to the formula. Wherever we see x, I'm going to replace it by x cubed. Wherever I see n, I will replace that by a half into the binomial series formula. Now, possibly, just so that you can see what is going to happen, I would, and I'm going to quickly write down the formula again. 1 plus x to the power n is equal to 1 plus n times x. Yes, do you remember n minus 1 over 2 factorial x squared, n minus 1, n minus 2, 3 factorial x cubed, n, where do I stop now? N minus 2, n minus 3, 4 factorial x to the power 4, and so on. Now, I haven't specified a term where you should stop, but let's see. We'll go up to the power 4. Okay, getting back to this. Therefore, 1 plus x cubed to the power of half. Wherever I see x, replaced by x cubed. Wherever I see n, replace by n, so that will become 1. N is a half, x is x cubed. Of course, the brackets. The next term, n is a half. Then a half minus 1 over 2 factorial. X is cubed, and that's all squared. Merely substituting. Wherever I see n, I put a half. Wherever I see x, x cubed. Continue. A half minus 1, a half minus 2 over 3 factorial. X cubed, all cubed. A half minus 1, half minus 2, a half minus 3 over 4 factorial, x cubed all to the power 4. And now take out your calculator, simplify. I get the square root of 1 plus x cubed is equal to 1 plus a half x cubed. Simplifying this, I get minus 1 over 8, and x cubed, sorry, all squared, x to the power 6. Then 16, x to the power 9, minus 5 for 128, x to the power 12. So the binomial series, if you can recognize it, and when you do recognize it, you can use the binomial series directly instead of using Maclaurin series and differentiating first derivative, second derivative, third derivative. As soon as you recognize the binomial series, you can apply its formula and work it out. Now, the next example, I am really just jumping the gun here in the sense that the very first step of this solution you may not have come across. In fact, we're going to do that in our next topic. So here we want to find a series expansion for arc tan x. Now, as it stands, it looks nothing like a binomial series. So applying our Maclaurin series, so in my solution, let's apply the Maclaurin series here. We're going to use Maclaurin, which means differentiate, differentiate, differentiates. But of course, we first substitute 0. So for arc tan x, f at 0 gives me 0. And of course, you can find that on your calculator, arc tan. Now, this is the step that I'm talking about. The first derivative, which you may not have come across just yet. So I'm going to put an asterisk over here. This step, you will derive this answer in the next topic. So why am I going to use it here? Let's see. The derivative of arc tan is 1 over x squared. Now, if you want to differentiate that again and again and again, you can use a quotient rule, or you can write this as 1 plus x squared to what power? Minus 1. And that derivative at 0 is equal to 1. Now look at that very carefully. I can find the next derivative. I can then find the third derivative, the fourth derivative. but inevitably I'm going to be using the product rule. So is there another way of differentiating the second, the third, the fourth derivative so that's much easier? Well, do you recognize something? Do you recognize that this is simply a binomial series where x is replaced by x squared and n is replaced. So x is replaced by x squared and n is replaced by -1, which means using binomial formula, I can write 1 plus, I can write this term, going back to binomial series formula. Do you remember that? There it is. 1 plus nx. So using that formula, I will get the first term, 1. Then -1 times x squared. -1 minus 2 over 2 factorial x squared all squared, and so on. -1 minus 2 minus 3 over 3 factorial x squared all cubed. And then simplifying that, I get 1 minus x squared. Just watch your calculations, watch your signs, minus x to the power 6 plus x to the power 8 minus and so on. So that is my first derivative. But using binomial series to simplify. So why would I want to do that? Very easy. Now I can find the second derivative, and the second derivative is so easy. What's the derivative of 1? That's 0. What's the derivative of minus x squared? Minus 2x. X to the power 4, 4x cubed. Then minus 6x to the power 5, 8x to the power 7. And what's the second derivative? At 0, I get 0. I can find the third derivative. Minus 2. Then 3 times 4, 12x squared. Minus 30, x to the power 4. Plus 7 times 8, 56, x to the power 6. Then I can find the third derivative at 0. And that gives me minus 2. Fourth derivative, 24x. Okay, I'm just going to write the next two derivatives. Once again, these are straightforward differentiation of the power rule. The fourth derivative at 0, 0. My fifth derivative is 24 minus 360 x squared. Yeah, I get 1680 x to the power 4. And my fifth derivative at 0 is equal to 24. Now, what do I do with this? Remember that I used a binomial series not from the original term, but from the first derivative. So I first used a binomial series to simplify the first derivative. Now I'm going to use the formula for Maclaurin. And the Maclaurin series formula is f of x, f at 0 First derivative at 0, x. Second derivative at 0, 2 factorial x squared, 3 factorial x cubed, so on. Therefore, my arctan of x, okay, what's my first derivative at 0? At 0. What is my first, sorry, f at 0 is 0. My first derivative is 1, so it will be 1 times x. Second derivative, here's my second derivative after I use the binomial series to simplify it. So that will be 0. Then minus 2 over 3 factorial x cubed, then a 0, then 24, 5 factorial x to the power 5. Simplifying there, I obtain my final answer for arctangent of x is equal to x minus x cubed over 3 plus x to the power 5 over 5 minus x to the power 7 over 7, and so on. There's the pattern established. Derivative of arctan, a little bit more intricate. You need to go through it once again. That brings